Hi everyone, welcome to one more of my lessons. Today's lesson is just me solving one of the problems, and this is related to electricity transmission. Now there are two similar questions in your booklet. So there is a worksheet which says New Zealand Electric Supply. I've worked through this, I've taken a photo and put that on the Google Classroom as well as on the Google Slides. There's also a similar question, which is question number 5 under mutual inductance, and I thought I'll work through that. Okay, so they both are similar. You've already got the worked out one, but I'll just talk you through it because there are certain things that you need to know, and that's important. So I'll just read through the question, and I've kind of done a diagrammatic representation pictorially to see what the scenario is. So power stations produce an alternating current at a voltage of about 25 kilovolts. So there's your power station. 25 kilovolts is 25,000 volts. Now this is stepped up at substations to 220 kilovolts. So this is a substation. It's stepped up to a much higher voltage. Okay, 220,000 volts. Now, and it is transmitted over long distances via the national grid. The voltage available to most consumers, that's a user, is 240 volts. Now, if the transformer at the power station has 80,000 turns in the secondary, how many turns are there in the primary? So in order to do this, where's my calculator? Okay. Calculator ready? Okay, so in order to do this, we just used NP, which is number of turns of the primary, divided by number of turns of the secondary, is voltage across primary over voltage across secondary. So the number of turns of the primary is voltage across primary times the number of turns across secondary divided by voltage across secondary. So the number of turns of the primary is voltage across this is 25,000 times number of turns of the secondary is 80,000 divided by voltage across the secondary, which is 220,000 turns. And then when you do all that, what you end up with. So 25,000 times 80,000 divided by 220,000, you get 9090.9. So that is about 9091 turns. So that's the answer to this part. Okay, the next one is to calculate the current in the transmission line. Now the current in the transmission line is dependent on two things. So one is the power at which it's transmitted and the voltage at which it's transmitted. Okay, so for this one we're going to use P equals V times I, or current is power divided by voltage. Your power is 40,000 watts. Your transmission voltage is 220,000 volts. So when you divide 40,000 divided by 220,000, you get a very small current, which is 0.182 if you want three significant figures, amps. Okay, so that's it. So the overhead transmission lines, the current is very small, but the voltage is very high, so you get the same power. Now what's happening is calculate the rate at which energy is lost as heat in transmission. They've given us this distance of 200 kilometers, and the resistance per kilometer is 5 ohms. Okay, so energy is lost as heat when charges travel through wires because of resistance, and charges traveling is your current. So the formula that we use in order to calculate the rate at which energy is lost, it is a power formula, but you've got to use the I squared R because to do with current and resistance. Okay, so the rate at which energy is lost as heat is I squared R, or power is your current squared is 0.182 squared, and the resistance for this whole thing is 5 times 200, which is 1000. Okay, so you get 100 and Okay, so it's 0.182 squared times 5 times 200, and I get 33.124. So about 33 watts. So your answer, sorry, 33 joules per second or 33 watts. Okay, so that's the power loss. So from 40,000 kilowatts, you lose about that much energy while transmission. The voltage, so that's the power energy lost in the form of heat. Now, because there's some energy lost, there's going to be what's going to be a potential difference or a voltage drop across the transmission line. So the voltage drop, you just use V equals I times R. So that's your voltage drop. Your current is 0.182 and your resistance for the whole length of that wire is 5 times 200. So you get 1,182, I think, 0.182 times 5 times 200. You get 182 volts. That's the voltage drop. And the question is this significant? And my answer would be 182 does sound like a big number, but if you compare it with 220,000, 182 is really just a small percentage of this. And the way I justified my answer was I did 182 divided by 220,000 times 100, and you get a very tiny percent. I don't remember off the top of my head, but it's 0.0 something. So it's just a very small fraction that is lost at the voltage drop. So it doesn't really matter. Okay, and then this last part, if the voltage had not been stepped up to 220 kilovolts, but it had been transmitted at 25 kilovolts, what would be the transmission voltage? What would be the voltage drop, the power loss, if the transmission or the power that's lost instead of 33 watts? So in order to do that, we first have to get the transmission current. So transmission current is power divided by voltage. Your power is still 40 kilowatts. So that's 40,000 divided by 25,000. So instead of 220,000, we're going to do 25,000, and you're going to end up with a bigger current, aren't you? So 40 divided by 25, you get 1.6 amps. Okay, now the power loss in transmission is to do with the rate at which energy is sent. It's to do with I squared R. So that's 1.6 squared, and your resistance is 5. Can you see this bottom? Yes. Times 200. So 1.6 squared times 5 times 200, you get 2,560. So 2,560 joules per second or watts. So what we are comparing is if the current is high compared to a small current, you lose a lot of energy in the form of heat. So that is why power is transmitted at high voltages and small currents, electricity. Okay, so I hope that made sense. Bye for now.